Good morning, afternoon, and evening. Welcome to Entangled Brilliance, Science, Bias, and Quantum Mechanics. Sponsored by the Center for Asian Studies at the University of Texas at Dallas, this program reflects the center's commitment to foster knowledge of and mutually beneficial engagement with the diverse cultures of Asia and Asian America across the spectrum of human activity. Our subject today is the life, scientific achievements, and continuing legacy of the physicist Chien-Shiung Wu. It was occasioned by the recent article in Physics Today about her trailblazing experiments in particle physics. I'm honored to share this virtual space with two of the authors of that article, Drs. Hsuan Feng and Chon-Fai Kam, along with UT Dallas physics professor Dr. Zhang. They will address her legacy primarily from a scientific perspective, focusing on what have been called Dr. Wu's two gems in a box of pearls. First, her famous parity violation experiment that shook the conventional understanding of symmetry in the physical world by revealing that a fundamental particle and its mirror image are not always identical. They will focus primarily on her second gem, the groundbreaking contribution to the concept of quantum entanglement that has, to quote the Physics Today paper, emerged as the cornerstone of the burgeoning fields of quantum information, quantum computation, and quantum technology. My role is to place her life and importance in larger cultural context. I'm not a physicist. My primary academic field is the Western cultural tradition from antiquity through the Middle Ages. Thanks to the intellectually vibrant environment of UT Dallas, my interests now expand to include two extraordinarily fruitful forms of convergence, of Asian and Western perspectives, and of the natural sciences, creative arts, and humanities with one another. It's my conviction that from the confluence of both unions will arise a generation of scientists, humanists, and artists capable of ever deeper, more subtle, and more insightful interdisciplinary ways of imagining and exploring the world, the universe, and ourselves. I'll begin by sharing some thoughts on the close relationship of scientific investigation with artistic creation and humanistic interpretation. Consider the words of Alexander Humboldt, arguably the most influential scientist of the late 18th and early 19th century. Nature herself is sublimely eloquent. The stars, as they sparkle in the firmament, fill us with delight and ecstasy, and yet they all move in orbit marked out with mathematical precision. Humboldt calls our attention to another kind of entanglement, the inextricable interaction of the sciences with the humanities and creative arts. His statement illustrates the principle that what is seen depends on the knowledge, intent, and perspective of the observer. That principle pulsates at the center of both ancient and modern thought. Consider the words of the 6th century of the Common Era philosopher Boethius, who wrote, "What is known is not comprehended according to its own nature, but rather according to the nature of the person comprehending it." And it is an inherent aspect of human nature to view the physical world, and especially the heavens, not only to discover and describe as precisely as possible the processes at work there, but also to find both aesthetic delight and intellectual inspiration there. Those complementary perspectives suggest the interaction of separate but complementary modes of thought, and therefore of symbolic expression. The model of human cognition that I offer here draws heavily on the work of the cognitive psychologist Jerome Bruner, anthropologist Ellen Dissanayake, and others. This model suggests that human cognition emerges from the continuous interaction of two modes of thinking: a logical analytic mode, that is, thinking guided by reasoned hypothesis that moves forward in careful steps and logical proofs toward a sound argument and empirical discovery, with an imaginative associative mode that leaps sideways, if you will, into the discovery or creation of connections. As the biologist Lewis Thomas once remarked, what scientists and artists have in common is the ability to see connections among phenomena that seem to most people unrelated. Meticulously developed mathematical proofs often follow such imaginative leaps. Werner Heisenberg called the corresponding mode of logical analytic expression, that is, the use of as static, that is, the use of symbolic language that leads to a strictly narrowed range of interpretation. For example, mathematical proofs, but also the verbal language of scientific explanation or medical diagnosis. He labeled dynamic the symbolic language, visual, verbal, and musical, of artistic creation that invites aesthetic and intellectual delight through imaginative expansion of possible meanings. This distinction underlies the different goals of a scientific theory and a story. The better the theory, the more opportunities it offers for disproof. The better the story, the greater the range and more opportunities it offers for interpretations. The two modes of thinking always coexist, varying only in proportion and intensity. Consider the interplay of scientific and imaginative language even in the Physics Today article, where my colleagues could not resist noting that parity violation suggests that, quote, sometimes nature can tell right from left. In another article, someone suggested that nature has a bias toward the left. Another example is the word entanglement that I've used in two different ways. Its technical scientific meaning differs from its social meaning. Both are mixed, after all, in Einstein's initial description of the phenomenon now called entanglement as spukhafte Fernwirkung, or spooky action at a distance. As a result, Heisenberg proposed that a complete and exact depiction of reality can never be achieved. Scientific theories will always be partial and provisional. In the words of the physicist Wolfgang Rindler, they are best regarded as models that don't assert an absolute truth, but rather an approximation to the truth. They don't tell us what nature is, but rather what it's like. The same holds true for any artistic creation or historical explanation. And for me, Humboldt's eloquent fusion of scientific curiosity with artistic appreciation and philosophic wonder provides a perfect entrance to my partial, provisional, and to a great degree admiring attempt to understand and portray Chien-Shiung Wu. How could I or anybody hope to do justice to a figure so complex and inspiring, so famous for her scientific accomplishments that she is known as the Madame Curie of China and the First Lady of Physics? Chien-Shiung Wu was born in a small town near Shanghai, China, on May 31st, 1912. Her father was an engineer and her mother a teacher. A metaphoric connection with Madame Curie began early. Her parents encouraged her to pursue scientific and mathematical studies, citing Curie as an inspirational model. Despite cultural restrictions on the educational opportunities for girls, she excelled and in 1930 enrolled in China's National Central University, now Nanjing University, where she majored in physics and graduated first in her class. While a student there, she studied with Professor Chien-Shiung, who had received his doctorate in 1933 for research supervised by Madame Curie. Wu managed also to become entangled in academic politics and became a student leader of sorts. At one point, she led protests that included a sit-in at the presidential palace in Nanjing that led to a meeting with Chiang Kai-shek. After graduation, she did graduate level study in physics and worked as a graduate assistant supervised by a female scientist, Gu Jingwei, who had earned her PhD at the University of Michigan and encouraged Wu to pursue her PhD there. She was an important role model for the young Wu, who took her advice and traveled to the United States. A quote from one of my sources writes, although she had originally intended to study at the University of Michigan, the sexual bias that she encountered in America For example, Michigan women at that time were not allowed to use the front entrance, appalled her, and she transferred to the more liberal environment at the University of California at Berkeley. In fairness to Ann Arbor, she later stated that she based her decision primarily on the superiority of Berkeley's science facilities that included the first cyclotron and the chance to work with Ernest Lawrence. At Berkeley, she studied nuclear physics, and there she also met, and in 1942, married another doctoral student in physics, Luc Chiao-Yuan. In 1947, they would have a son, Vincent Yuan, who also became a distinguished physicist. She and her husband began their American academic careers in 1934, he at Princeton University and she for a while at Smith College. But after a few years at Smith, she was appointed as the first female instructor on the faculty at Princeton's physics department. In 1944, she joined the Manhattan Project at Columbia University, where, in addition to other notable contributions, she helped develop the process to separate uranium into U-235 and U-238 isotopes. She spent the rest of her career at Columbia as, quote, the undisputed leading experimentalist in beta decay and weak interaction physics. She would later describe beta decay as an old friend with whom she spent many hours. Her first great contribution, as many here know already, was the pivotal experiment involving beta decay that provided the seed from which quantum mechanics could sprout. Here I'm going to quote primarily a published account. While at Columbia, she was approached by two physicists, Drs. Chong-Dao Li and Chen-Ning Yang, about the quantum law of parity. The two physical systems, such as atoms, are mirror images and behave in identical ways. They theorized that parity was not conserved during beta decay. She then spent months conducting sophisticated experiments that supported their theory. In late 1957, Drs. Li and Yang were awarded the Nobel Prize in Physics for their theoretical contributions, while Dr. Wu's experimental contribution was overlooked. Another word would be slighted, or even, as one essay states, inexplicably omitted. Perhaps the omission was not inexplicable, we've learned. An explanation is to be found in the recognition that people, like nature, can exhibit bias. In this case, the gender-based bias in which she was entangled throughout her career. Bias that she called attention to and actively sought to change for other women and coming generations. At a symposium at MIT in October 1964, she stated, I wonder whether the tiny atoms and nuclei, or the mathematical symbols, or the DNA molecules have any preference for either masculine or feminine treatment. On another occasion, she spoke directly about her experience with gender bias in America. It's shameful, she said, that there are so few women in science. In China, there are many, many women in physics. There's a misconception in America that women scientists are all dowdy spinsters. This is the fault of men. In Chinese society, a woman is valued for what she is, and men encourage her to accomplishments, yet she remains eternally feminine. But she also managed to express her concerns and difficulties with good humor, as when she remarked that the only thing worse than returning home from the lab to a sink full of dirty dishes is not going to the lab at all. Some challenges and biases she overcame. At Columbia, she was promoted to associate professor in 1952, and then in 1958 to full professor, the first woman to hold a tenured faculty position in that physics department. As I mentioned, she worked forcefully to enable other women in science to conquer, or even better, not to face similar obstacles. In her career, she received numerous honors and tokens of recognition that would range from the inaugural Wolf Prize and the Comstock Prize in Physics to an asteroid named after her. After Wu retired from Columbia in 1981, She devoted much of her time to educational programs in the People's Republic of China, Taiwan, and the United States. She was an intense advocate for promoting girls in STEM education and lectured widely to support this cause. In recognition of those efforts, in 1998, unfortunately a year after her death, she was inducted into the American National Women's Hall of Fame. And she is still widely revered, especially in China, as a role model for young women scientists. It proved impossible, I must confess, to read and learn about Madame Wu without increasingly admiring her and wishing that I could have met her. Hers is a story that indeed invites multiple layers of response. Inevitably, as a professor of classical and medieval Western literature, I began to see her story as a heroic quest for enlightenment, hindered less by enemies or monsters than by societal biases that kept her from science's holy grail. As a reader, I responded with particular admiration to this episode. Soon after she had been approached by her colleagues Li and Yang, she had begun thinking about her parity violation experiment. Although scheduled to travel abroad with her husband, she canceled her flight at the last minute and told him to go on ahead without her. She had wanted to start the process of experimenting because she knew others were and would be thinking about it, and she was not about to be bested. To complete this all too partial and provisional presentation, I turn again to Wu's own words as she described her response to the success of the parity violation experiment. There were moments of exhilaration and ecstasy. A glimpse of this wonder can be the reward of a lifetime. Could it be that excitement and ennobling feelings like these have kept us scientists marching forward forever? This statement evoked in my mind the association with Humboldt that began these remarks. Both Humboldt and Madame Wu emphasized the pleasures of questing for scientific understanding combined and connected with artistic appreciation. Humboldt spoke of delight and ecstasy, Wu of exhilaration and ecstasy. In both these brilliant and daring scientists, we see a sense of wonder, of excitement, and of scientific investigation, like all true loves, as an ennobling experience. My admiration also awakened me to the great absence in her life, the title of Nobel laureate. In my quest, I found valuable, if scattered, information on the web and in essays. However, what I did not find was an adequate, thoroughly researched biography of Madame Wu, because none exists. Not in Chinese, I am told, and in English, there exists only an illustrated, though quite well-written, book for children ages 5 to 10. Slighted by the Nobel Committee, she deserves better from those of us fascinated by the history and philosophy of science. A thoroughly researched and nuanced biography would be an important addition to the literature. While her story evokes in part thoughts about entanglement and bias beyond their scientific implications, it also provides a glimpse into an extraordinary intelligence, persevering spirit, and complex life. She was, after all, far more than a scientist. She was a daughter, a wife, a mother, a mentor, a human being, a grandmother. And I'll leave the last word to her granddaughter, Chien-Shiung Wu's granddaughter, who wrote here's how she described her. My grandmother was wise, discerning, with her hair in an elaborate updo that was its own achievement in physics. She had that mischievous half smile that always made me wonder what she was thinking. Chien-Shiung Wu was, in summary, a profoundly inspirational human being who cannot be fully understood or adequately described, as well as a brilliant star sparkling in the firmament of science. And now it's my pleasure to ask Professor Zhang for his thoughts on the implications and impact of Madame Wu's scientific inquiry. Dr. Zhang.
Okay, all right. First of all, I would like to thank the Center of Asian Study at the UT Dallas, to organize this wonderful, forum to discuss the legacy of Chien-Shiung Wu, and in particular this quantum entanglement. It's really my honor to be part of that. And in the next 10 to 15 minutes, so what I'm going to do is based on my own perspective, we try to disentangle this quantum entanglement. And basically, to understand, entanglement states, we have to first of all understand something slightly trivial. That's what we call a product state. So, during the preparation of this slides, I try to think, how to explain this to my daughter, who is actually 6 years old. Okay, I figured out that this is actually the best way to describe what is a product state and what is the entanglement state. So today, my daughter Evelyn and her best friend Ariel will have a play date. So for both of them, Elsa and Anna are kind of their favorite, princess, Disney princesses. Okay, so they always prefer to wear Elsa and Anna dresses. And okay, so here is this scenario one. So suppose my daughter Evelyn and her best friend Ariel, they do not play together today. Okay, therefore, so whether they choose Elsa dress or Anna dress is kind of independent, completely independent. So in this case, if I may use a mathematical formula to describe how they wear today. So here's the formula. So okay, so there is a cross product in the middle of the equation that basically tells Evelyn's dress today and the Ariel's dress today are completely independent. Okay, if we look at this bracket for Evelyn, so there is a sum. So basically it's depends on how you measure, right? Whether you measure on Monday or on Tuesday. So Evelyn may choose the dress as Elsa or dress as Anna. So this is kind of there are two possibilities. It depends on when you measure that. Okay, so this is also true for her friend Ariel. So Ariel may choose to dress as Elsa or dress as Anna. Okay, depends on whether it's Monday, Tuesday, or Wednesday. Okay, so there are two possibilities. So what I try to emphasize here is that so Evelyn's choice and Ariel's choice are completely independent of each other. So in this case, we call this state is a product state. So there therefore we can go forward and think about it. There's another scenario. So this is what I call scenario two. So in scenario two, so if my daughter Evelyn and her best friend Ariel have a play date today, for example, they decide one of them will dress like Elsa and the other will dress like Anna. Okay, so therefore their choices are not independent of each other. Okay, so therefore we end up with two possibilities. So that's why in the middle of the equation I have a plus sign here. Okay, so the first term, that tells us the first possibility. The first possibility is that my daughter Elsa chooses to dress like dress as Elsa, and Ariel chooses to dress as Anna. Okay, that's the first possibility. The second possibility is my daughter chooses to dress as Anna, and then Ariel will choose to dress like as Anna. Okay, so this is the second possibility. So if you really measure, right? If you suppose I really measure one of the two girls. Okay, for example, they have a play date today. Today together, and one, let's say at 3 p.m. one goes to the pool, the other one goes to school. Okay, but they still dress in whatever they choose in the morning. So if you really look at what Evelyn dressed, then you can actually predict what Ariel has dressed today. Okay, so this is what we call a entanglement state. Okay, so what actually Dr. Chien-Shiung Wu discovered in 1949 is actually exactly the same as this equation I just illustrated. It's an entanglement state. So of course, human beings are classical objects. So to understand, the state, Chien-Shiung Wu discovered in 1949. So we have to do some, replacement. For example, we have, replaced avalanche and arrow by actual quantum particles. So for example, photons, two photons, photon 1 and photon 2. So of course, the alpha and addresses are going to be replaced by the actual quantum states. So in this case, for example, we can think about the polarization of light. So one possibility is, the horizontal polarization. The other one is the vertical polarization. Okay, so if we do that in two replacements, so this state will become this. Okay, that says, there is a entangled state of two photons. The first photon, if the first photon is in the horizontal polarization, then the second photon will be in the vertical polarization. If the first the photon is in the vertical polarization, then the second photon is going to be in the horizontal polarization. Okay, so this is exactly the entangled state, first discovered by Chien-Shiung Wu in her wonderful experiment. What actually happened, around that time is that, roughly in 1946, Dr. John Wiener suggests that, people to study the polarization of pairs of gamma ray photons produced by electron position annihilation. Okay, during that annihilation process, two photons are produced, and turns out they are actually in a entanglement state, and that entangled state is a single state. To measure, to demonstrate that prediction, it requires to measure, these two photons. So then, 3 years later, in 1949, Dr. Chien-Shiung Wu and her student, carry out a beautiful experiment. And this is a picture I got from the article published in Physics Today last year by another of our two speakers. So basically, in the center of the figure, you can see, there is an electron and the positron. They can have a kind of so-called annihilation process. So of course, energy needs to be conserved. Once the positron and electron disappear, their energy becomes the energy of photons. So in this case, there are two gamma ray photons generated. And what's interesting is, first of all, these two gamma ray photons are kind of entangled in a single state, and it's very interesting. That's to be measured. Second of all, these two photons, even though they are entangled in a single state, but they can be far away from each other. Therefore, we can independently measure these two individual photons at different locations. So in this figure, that is one on the left and one on the right. So this is, by that kind of experiment design and experimental demonstration, Dr. Chien-Shiung Wu and her student, demonstrating, we do have, entanglement states for the first time. So that marks the year, 1949. Okay, so in the next, couple of minutes, I'm going to show you how beautiful and how complex this entanglement can be in the quantum regime. So for example, let's think about it. We have, a electron gas in 2 dimensions. So let's apply a perpendicular magnetic field to the system. So in this case, the motions of electrons are kind of quantized into localized cyclone orbits. So what's interesting is that in the quantum regime, so there is 1 electron per orbit. Okay, so 1 electron per orbit. This is required by in the quantum regime. So for a typical sample, a typical 2D electron gas system, for example, with a size of 1 millimeter square. So in this case, for this size of sample, roughly speaking, there are 3 times 10 to the 10 electrons. So these electrons are kind of quantum particles. They are indistinguishable. Okay, so what's interesting is, let's consider a case, so when this, when all the orbits are kind of 1/3 filled. So that means, we can choose, 10 to 10 electrons to fill 3 times 10 to 10 spots. Okay, those spots are the cyclone orbits. So in this case, we have to ask a question: how many independent choices do we have? So the answer is, if we want to, select 10 to the 10 electrons out of the 3 times 10 to the 10, electrons. So therefore, this number is very, very large. Is roughly speaking is 10 to the 10 to the 10. Okay, this is extremely large number. And what I try to say is, so in this case, there is the a many-body entangled state, and that entangled state is astonishingly entangled, and it shows us the beauty and the complex of entanglement. So first of all, in this the simplest entangled state discovered by Dr. Chien-Shiung Wu, there are only 2 particles. There are only 2 kinds of states, right? So however, in the example I just show you, so there are 10 to the 10 number of particles. So basically 1 and 2 is going to be replaced by 1, 2, 3, 4, 5 up to 10 to the 10. Okay. So second, in this simplest entangled state discovered by Dr. Wu, there are only 2 terms, basically 2 possibility. But in the case I just illustrated, there is a quantum superposition of 10 to the 10 to the 10 different states. That tells us how long the equation will be. Okay, so remember, this is not a simple sum. This is the quantum superposition of 10 to the 10 to the 10 different states. So basically, this tells us, the beauty and the complexity of a entangled state. So by the way, this is one of the very famous fractional quantum Hall state. It's called 1/3 quantum Hall state, also called Laughlin state. Laughlin won the Nobel Prize in 1998 because of this discovery and the explanation of the experiments. So I do want to mention the quasi-particle of this fractional quantum Hall states is actually something we call anyons. So anyons only occur in 2 dimensions, and they are neither fermions nor bosons. Okay, so if you interchange 2 anyons, so you neither gain a minus sign or a plus sign. You gain a phase vector. Sometimes you even gain a matrix. That is non-abelian case. Okay, so I'm going to stop here with the scientific discussion about what is entanglement, and why entanglement is beautiful and why is that complex. Okay, so with that, I really want to see that Dr. Chien-Shiung Wu's brilliance lead to the discovery of and the demonstration of entanglement state. Okay, so as actually one of the reasons from my perspective is why she is the first person to demonstrate entangled state is because she has entangled brilliance. So that entanglement is an entanglement of Western culture and Eastern culture. So that significant entanglement lead to the demonstration and the discovery of entangled state. So because of that, the chapter on entanglement continues. Thank you for your attention.
Excellent.
Dr. Kam.
Yep. So my time this afternoon, I'm in Germany, so I will tell you something from my own perspective. What is the quantum entanglement? Okay, and if you want to know more technical details, you can read my book and also the physical.
Go to the next screen.
Yep. Okay, so in the textbook, you will see many times depict the atom. The atom is a spinning small particle, just like the Earth spinning around the sun. But actually, this picture is not correct. This is the wrong picture. This is the very classical picture. And in quantum world, we have quantum probability wave, and the right picture is the correct one. So actually, atom is a three-dimensional probability wave. Even this picture is not 100% correct, but this is the most closely picture of what is an atom. It's a wave. And our human actually, to the end, are also quantum particles. The only difference is that we human has a very, very localized quantum wave, and our quantum wave does not spread out. And for tiny, tiny quantum particles like atoms, their quantum wave will spread out in the larger space. So everything actually is a quantum wave, just how it spread and how it localized. This one. Okay, in the 1935, there's the first paper talking about this phenomenon of entanglement, and that's proposed by Einstein and his assistant Rosen and Porofsky. And in their thought experiment, that's like this: you have two quantum probability wave that initially get in touch, so that they have overlap and they allow each other. And afterward, they separate long distance, but still keep in touch so that the information is still there. That's why if you measure the first quantum probability wave, you immediately know the result of the second one. The second quantum probability wave even is far, far away from the first one. This is what Einstein calls spooky action at a distance. This page. And at the same year, just immediately after the EPR paper, Schrödinger wrote another paper on this phenomenon, and he considered the concept of alive and dead cat. And I show you that paper in some red color, you can see the simultaneous live and dead cat. That's what he say. And in the German work, entanglement, here to describe also, some strange thing. But I can tell you in the next slide, this one. It's not strange thing. The fundamental reason is that everything are made of quantum wave. So if you have a box, imagine you have a box, a closed box. You know it inside, there's a box, there's a cat. And the cat is also a quantum particle. So quantum particle or quantum probability wave could be alive and dead simultaneously. It's only upon you open up the box, you will see a cat inside known to be either alive or dead. That solves the problem. So that's not something magic. It's the fundamental physical concept of everything is made of quantum wave. Next one. And years pass, now the quantum mechanics is not only textbook things, it's bring forth the phenomenon of entanglement to the real world, and you can see real quantum particles sharing this kind of hidden dialogue. And this entanglement becomes the fundamental phenomenon in all kinds of quantum technologies. For example, you see it in the quantum computer, and you see it in quantum communication and quantum sensing, etc. For example, in 2017, there's some quantum communication experiment over 1,200 kilometers between the Earth and the space, their satellite in the space. And just a few weeks ago, they did the same experiment, but 10 times larger distance. Now the distance is 10,000 kilometers and 13,000 kilometers. And both experiments are done by Zhang Pan in the USTC in China. This page. And it is exactly the importance of the quantum entanglement brings these two physicists the Nobel Prize in Physics in 2022, and award to Alan Expert, the John Kratz and Anton Terlinger for the experiments with entangled photons, establishing the violation of Bell inequalities and pioneering the quantum information science. And next page. And it's exactly where Chien-Shiung Wu did her unique contribution in the 1946, just a few years after the EPL paper. John Wigler proposed experiment like this, already discussed by another speaker. Then the light coming from the electron anti-electron pair, a high energy gamma wave, and more importantly, they are entangled gamma wave. So the photons are quantum particles, so they can entangle it. And in the 1949, Wu and her student Sokolov, did this beautiful experiment and experimentally precisely verify the photon entanglement. So nowadays it's called the Wu-Sokolov experiment in 1979 and published in 1950. It's the first, historically, the first photon entanglement experiment, just 15 years after the EPR paper. The next page. So I will conclude my talk with this small poem written by myself. So in the past, people built large accelerators to seek the truth on the smaller scale and higher energies. But to me, the universe is just a symphony of all things. What's the significance of breaking a single note? I care more about the relationship between the notes, and the essence of physics are the music of existence. Lying this. So entanglement requires no energy to persist, just like the inertial motion demands no energy to continue. And the universe requires no energy, so I remain powerless. Thank you.
Excellent.
Okay, that's the appendix. Okay, if someone asks, I will show.
Well, I'm going to ask.
Okay.
In the citing the Nobel laureates, one of the words that they use is Bell inequalities.
Yes.
You obviously thought a lot about Bell inequalities, and I suspect you even prepare some presentation here.
Yes.
Can you quickly tell us what Bell inequality is?
Yeah. This page, I prepare something. Yeah. So it's Bell inequality is something that he takes Einstein's concept of local realism. So these two concepts. One concept is called locality. That means there's no spooky action at a distance. And the second concept is called realism. It means that the physical properties exist before measurement. You measure something exist before your measurement, independent of your observation. That's called realism. And next page. And this, the original inequality, this can be experimentally verified. If this inequality is violated, then the two concepts combined together must be wrong. Next page. Yeah, so this is the mathematical formalism of the inequality that can be experimentally verified, and the real experiment do support the quantum mechanics and so that there's some kind of non-local correlation between quantum particles, go beyond all the classical explanation. The next page. And so what are non-locality and non-realism? So non-locality means that indeed there is spooky action at a distance. And what is non-realism means that the physical property do not have definite value before measurement. In fact, they only come to existence when you do the measurement. Yeah, that's it.
Thank you. Back to you, Dennis. No, your sound.
Yeah,
You're muted. You're muted.
Yes. I'm listening with and would like to hear from anyone in the who's tuned in with the mixture of scientific precision and poetic association in Dr. Kam's remarks, that it seems the closer we get to quantum issues, the more we must resort to poetic language. The notion of an internal dialogue between particles. And the idea of the particle as a wave is very much like the notion that those of us involved in translating from language to language, the way we approach language is not a collection of particles or a collection of words, but the words form a kind of wave that can only be understood in connection with each other. So that, and as a musician, you don't play a series of disconnected notes that happen to be together, but they take on a reality of themselves, an entanglement depending upon the other words near it, and the person reading it will mean different things. So it seems to me that I was fascinated by the closer connection than I had seen previously of physics theories with reading poetry.
Let me introduce someone in the audience. I think his name is Peter Maloney. He is from the University of Rochester, and I think he's formerly at Los Alamos. Peter, are you still there? Can you say something? You need to unmute if you're still there. Well, before we get to him, Kam, since you're the one that wrote the end of the poetry, that obviously Dennis is very much inspired. Can you say something more about what you wrote in that poetry, in the poem?
Yeah. I first wrote it in Chinese. Yeah, it's the English one is the translation. And in Chinese, actually it's the same word. Okay, so it's called Wu Lang. Okay, so no energy. Okay, and powerless, the same word, Wu Lang. So in the Chinese language, it will be more interesting. They are the same word.
But doesn't that imply the notion of reading as bringing things into existence from the standpoint of the observer, that is the reader? And
yes,
so
yes.
it's that the meaning only comes into existence when read. And
yes.
when you, as you say, I wish I could have read your poem in Chinese,
Okay.
Just as the two translations from the original German of Humboldt's works gave slightly different interpretations of nature because the languages they were using were different, and math is a language that enables us to see in a certain way.
Yeah. I like your comment. Yeah. So the physics is not something that you gather the facts, but they are something can be organized beautifully like poetry. Yeah. And that's to me, that's the quantum theory. The classical view is that you just have isolated existence, but now you see actually it's not everything connected or entangled.
Is it not true that we are all quantum particles? I mean, Dennis is a quantum particle.
Yes.
He's made of quantum particles. You know, if you break him up, he's nothing but electrons and atoms and so on.
Yeah. Everyone.
And so therefore, Dennis and I can have entanglement.
Yes.
Except that entanglement we don't have an experimental system to measure it. Is that correct?
Yes, absolutely. Yeah. So entanglement is it between any objects, just weak or strong. And currently we only can detect strong entanglement, and weak entanglement, that's for the future.
I actually have a question for Dr. Zhang. If you're he's still there.
Yeah, I'm here. Yeah.
You know, people such as Wu and Sheknoff have to find some quantum particles, as in their cases, photons, to look at entanglement. What you're suggesting is that in nature, there are particles that you don't have to do extra work, and already entanglement can be shown easily. Is that what you're trying to say?
What I try to say is the entanglement is everywhere, and particularly when you consider many body states. So however, in many cases,
why many body states? Why not two body states?
Okay, two body states is the simplest of many body states.
That's right.
So that is why people talk about when people discussing entanglement, they always use this two body kind of entanglement state. So the reason is that is simple to illustrate, that is simple to measure, and that is simple to prepare. So the state I discussed in the end of my talk is really a beautiful state. People can probe it, people can calculate that, but however, people haven't really measured the entanglement of that state. It's just like it's too complicated to measure the entanglement, and the entanglement level is very, very high.
Very good.
Now, back to the comment, Dennis and you in the conformal entangled state, that is absolutely correct. So, but one thing we have to keep in mind is that this entangled state is a superposition of many product states. So because because we are still living in the classical world, that means amount of within the product states in the superposition. So one of that has the highest probability to be measured.
Very, very good. I have another question for both of you. You're all deeply in this field. In 1926, there was a famous conference where all the big shots were there, Schrödinger and Einstein and Heisenberg and probably Bohr and so on. And at that time, there were three interpretations of quantum mechanics. One by Schrödinger, one by Heisenberg, one by Bohr. My understanding, it was that conference where people gathered together and eventually came to the conclusion that all three approaches were the same thing. So therefore, in some sense, what they're saying, quantum mechanics is a way to describe our physical universe. In the same way, Newtonian mechanics is also a way to describe our physical universe. In fact, it's the same physical universe. Why is that so difficult to go back and forth between classical mechanics and quantum mechanics? Isn't that the heart of the question, why in classical mechanics I do not see entanglement?
Well, that is because in the classical mechanics, quantum mechanics is certainly more fundamental. So you can go to one limit of the quantum mechanics, you will get classical mechanics. So during that approximation, okay, and certain information is lost. So therefore, you cannot go back from the classical world to the quantum world. That you can take a limit from the quantum world to the classical world.
Kam?
Yeah, the heart of the core of the quantum physics is the entanglement, and and it's there, but it's weak if you separate long distance. So in our scale, just what you mentioned, we cannot measure it. We still have not yet have some smart way to measure it, but it doesn't mean it does not exist. So if in the future we have better equipment, then we can measure the entanglement between the microscopic objects. Then you see actually our daily life also governed by the quantum mechanics.
Well, it's sort of not satisfying because going from quantum mechanics, classical mechanics, there should be a sliding rule where if you slide into that number to a certain number, it is in quantum, and if you slide it away, it should be classical. As far as I know, there is no such sliding rule. There are people saying that, well, let H bar be 0. But H bar can never be 0. It's a constant, which is a Planck constant. So we really don't know how to go back and forth between classical mechanics and quantum mechanics. Is that right?
Yeah. It's hard. Yeah, it's deep problem. Yeah, I cannot give you a definite answer.
But love to hear Dr. Zhang's comment on this.
Well, I think certainly we can go from quantum to classical. So, but we cannot go from classical to quantum. So as I said, there is this, for example, phase information, the interference information, that is lost when you're doing this. H bar goes to 0 limit.
Yeah, but H bar cannot be 0.
Yeah, H bar cannot be 0. That is, when you are living a world, the noise and the fluctuation is much larger than H bar. Then H bar is 0. So physics is about approximation.
Okay. Well, Dennis, back to you.
Oh, as I'm listening, I'm reminded of a question I brought up in one of our earlier conversations about that place where I think in terms of Newton and Einstein. And I've read that, Newton works perfectly. Newton's model works perfectly under certain circumstances, but as the speed and the distance become more massive, you must use Einstein's model. And somewhere in the middle, where the mass and the speed reach a certain level, neither would work. And is there a place where you can't be certain? I'm reminded as I listen, I'm particularly to Professor Kam, if the universe is, if you will, a prose creation, it can be understood in one way. But if it is, as Professor Kam suggests, a symphony, then to understand it, you must approach it from a different perspective.
Yeah.
And I'm back to Heisenberg's static and dynamic language. Is it ever possible to have one explanation? Because you can have one hopefully scientific explanation, but that omits the perspective that looks at the universe as a story.
Yeah, absolutely. Yeah, that's what I'm thinking about. Yeah. There's some other equivalent way of quantum theory that's called relational quantum mechanics. That's more like the view that you described. Yeah, and yeah, that's go too far. Where it's still developing. Yeah, and yeah, I try to understand quantum mechanics in this way. More like a symphony. Okay, more than you breaking a single note.
Well, let me try again. Peter Maloney, are you still there? Okay, he's not.
Can you hear
Anybody
me?
else? Sorry?
He's here. He's here.
This is Peter Maloney. Can you hear me?
Yes.
Yes.
Ah,
Oh,
Peter.
I'm sorry.
Well, let me just
I had a
introduce
problem on
who
my other
Pete-
device with my speaker, so I switched. I'm now on my cell phone. Thank you.
Okay. Let me
I'm
just
sorry
introduce
about this.
you who Peter is. Peter is a very well-known physicist who is, I think he's currently at University of Rochester, but he was also very important at the Los Alamos National Laboratory. Peter, I think we would love to hear your comments on this discussion.
Well, thank you. I'm enjoying it very much, and I really love your Physics Today article. But regarding
Well,
the
I
first
like
speaker,
your comment too.
thank you.
That you submitted to Physics Today.
The first speaker said something which I found very appealing. That the question of whether in physics, in science, we have a description of nature or have an understanding of what nature really is. So I was wondering, in the context of the EPR, spooky at a distance and action at a distance and so forth, Einstein is often said to have objected to the probabilistic nature of quantum mechanics. God doesn't play dice. But as John Bell emphasized, it wasn't so much the indeterminacy of quantum mechanics that Einstein disliked, but rather the seemingly lack of objective reality. I wonder if anyone on the panel has any comments on that, or did Madame Wu ever address such a philosophical question?
Cam?
Yeah, I guess at her time, that entanglement is not a central subject. Okay, this only in the last 30 years it becomes more and more advancement, and yeah, people start to discuss the topic like what you described, and yeah, so I don't think that Einstein is correct. Like, if actually he's wrong and wrong in many perspectives, I can give you two examples. One example is a 1986 paper. There's a paper titled that even the vacuum will violate the Bell inequality. I don't know whether you read it or not. So if you have a way to measure the vacuum fluctuation in the long distance, you will see that it also violates the Bell inequality. Yeah, so even the vacuum is not something that's so classical, it's also quantum. Yeah, and also another phrase is that there's a mathematical proof is that the spooky action at a distance, you thought that it only you see the spooky action at a distance, but actually it's not. It's that every observers, okay, you have finite speed to the left or finite speed to the right. All observers, infinite observers, all see the same thing. That is the spooky action at a distance with no time. So for me, it's very very strange. If our mind is by nature more classical mind, how can we understand such thing? But it happened. So that's why quantum mechanics is important. Nature behaves this way.
Of course, we cannot use that spooky action at a distance to communicate faster than light. There's no violation of special relativity, as you all know, of course. An anecdote, maybe, or comment. I've always felt in reading Einstein, the EPR paper, and what Einstein wrote later, that okay, this is controversial, I know, but I don't think Einstein would have been surprised by the Bell inequality experiments. I've discussed this with Clauser, Aspect, and Zeilinger. They all violently disagree with me in a friendly way. But Yakira Harnoff, who played such a seminal role in this field, says, of course, Einstein would not be surprised. He was just saying that quantum mechanics is peculiar. I don't like it. We need something better. But, I think in the EPR paper, they said this is what will happen experimentally. I don't know if anybody has... I know this is controversial. If anybody has any comments on that, I'd like to hear it. It's a little bit off track because I know we're supposed to be talking about Madame Wu, but you know.
Well, actually, it's very interesting. Our Physics Today article has really kicked up storm, Peter.
Great.
More and more people are now organizing conferences such as this one by Dennis, who is anything but a physicist. Got so excited about this and wanting us to talk about this today. I hope that we will begin to really rethink the issue between quantum mechanics and classical mechanics. I always gave the example, Peter, I don't know whether you agree with me, between a special relativity and quantum mechanics and special relativity and classical mechanics. There is a dimensionless number called velocity divided by the speed of light. If V over C approaches 1, then you go into relativity, and you move away from 1, you go into classical mechanics. Even the equations, you can show it that way. But between quantum mechanics and classical mechanics, there is no such number to slide back and forth. I know that people want to talk about, Planck constant going to 0, but a constant cannot go to 0, which is unfortunately true. So what do you think about that, Peter?
I agree with you completely. There's, of course, the argument from decoherence, that you go from, you see things in a classical way because of decoherence in the environment and so forth. But I agree completely with your remark.
And even to this day, around 1979, there was a paper that came out showing that classical equations, if you run it, it will go into bifurcations, and eventually will look chaotic. So people thought that maybe that's one way to understand quantum mechanics and classical mechanics, but that never really reached the final stage of understanding.
Yes, I mean, when we make a measurement, we always have to use a classical, macroscopic device, and
unfortunately,
we amplify noise, and that gives decoherence and so forth. It's another anecdote. When John Clauser, when he was doing his original experiments, visited Richard Feynman, and Feynman threw him out of the office. He didn't want to hear about it. Anyway, but I'm really glad your article is, eliciting a lot of discussion. That's terrific.
Yeah. Well, it really deepens our understanding or misunderstanding of quantum mechanics. Well, I think we're about, Dennis, do you think we're about time?
Yes, I lost some form of spooky action in the internet. Cost me 5 minutes of the conversation, for which I apologize. But I'm again fascinated by the notion that what we know, I think I got this learned this from Gadamer's uncertainty notion, that to investigate anything, you have to have a method.
Yeah.
And whatever method or whatever language or whatever perspective you choose both enables knowledge and limits the knowledge to that available to that method or that language or that approach. So to me, it's a non-question, will we ever come to a complete understanding of nature, such as Heisenberg said, we will mix languages, okay? I recently read with my students a magnificent novel called The Heart by the philosopher Melis de Carangal, who, it's about a heart transplant, but she says at any moment, the heart is either a physical pump or the heart of the human soul. And it is always both, but never conceived concurrently as both. And that's what, as a humanist, just fascinates me about physics. That it gives an unerringly ever more accurate, ever more intriguing notion of reality, and at the same time, um, such as the way my father taught me how to swim many years ago by steadily moving backward as I approached him. The more we know, the more I think we have to acknowledge there never will be a complete understanding. And that's the pleasure, that's the wonder that I hear Madame Wu expressing.
Okay, okay. I only have 3 slides. One of the things that I learned later on in my physics career is the so-called history of science. When I was a graduate student, there was a professor sitting next to my office whose expertise is history of science. As a young and, I guess, unruly graduate student, I always thought that what a waste of time to have a professor wasting his time on history of science when there's so much excitement that one should be talking about. As I grow older, I began to realize how distorted we are about our understanding of science until I heard a talk given by a professor somewhere in Taiwan about how difficult it was for Newton to show that simple F is equal to ma really works. You know, we tell our kids, oh, there's Newton sitting under the tree, apple tree, and an apple dropped on his head, and I understand. And then, you know, suddenly Newtonian mechanics came out. It is hardly there at all. So I would like to sort of use this particular example of quantum entanglement story as an important study of the history of science in general, but for me, how it became so important in my mind. Next slide. Well, we know that, we said that already many times today. Li and Yang got the Nobel Prize in 1957, and I'm so daring here, I put Wu's picture right next to the two of them, just to say that without Wu's work, neither of them will win the Nobel Prize. I think no one will dispute me on that fact. But let's come back to how her work, not in the parity non-conservation, but entanglement came out, at least as I am concerned. It came from one picture, and that's the next one. About 8 years ago, I was visiting Yang's in his home in Beijing, in Tsinghua University. My good friend, who is a good particle physicist, is a member in his team. We were office mates together at the Niels Bohr Institute almost 50 years ago. And during our discussion, just like this picture shows, for some reason, I just thought I asked Yang, well, Professor Yang, what do you think of this hot subject that people are all talking about, entanglement? And he looked at me almost just like this picture. He said, you know, who was the first person who experimentally verified entanglement? My mind just got, you know, started to act, you know, I said, oh, could it be, who could it be? I said, well, could it be the first person I really heard a lot about from about entanglement? It was Murray Gell-Mann, but it cannot be Murray Gell-Mann. He was a theorist. He wouldn't do experiments. Anyway, Yang immediately said it was Wu. It was published with a student in a paper in 1950 Physical Review. He said, I don't remember how to get it, but you can dig it up. Well, we digged it up eventually, and it led to this Physics Today paper eventually, which tells me that all our human interactions, not like apple dropping on the head of Newton, which nobody can verify whether that's true or not. We need to have clear understanding and verifiable, not only the experiments, but verifiable events of how things evolve into what it is today. Yang said that when, he was already, he may look young there, he's already in the 90s, mid-90s. Today, he's 103. He's still alive and kicking, okay? And for Yang to remember a paper published by Wu in 1950 in the Physical Review, granted, he didn't remember the precise citation, but he remembers it was 1950, tells me that this aspect of science, this aspect of quantum mechanics, as a physicist, was important to him. If that is the case, then I cannot possibly be the first person he told this to. And yet, I'm so proud of myself because when I heard that, it struck me so hard as to this whole concept of physics history, the history of science, that I just cannot let go. And I worked with my friends and so on. Eventually, our Physics Today paper came out. The Physics Today came out in 2025. Remember, Wu passed away in 1996, was it right, Kam? I think it's 1996. And this is many, many years after she passed away, and yet Physics Today is willing to put her picture and this point about her on the front page of Physics Today tells me how important her work is. And so it gives me even additional responsibility to make sure that everything I say, not just her experiment needs to be verified, but everything I say is scientifically, historically verifiable. And this is my understanding now of the importance of history of science. Thank you for today's meeting. I think I certainly learned a great deal. Dennis, do you want to have a final word on this?
No,
Dennis?
my final word is thank you to Hsuan for entangling me years ago with Asia, and with the implications of physics and science for the humanities and arts when they converge.
Thank you.
Thank
you,
you all.
everybody. Especially thank you, Peter Maloney, for your last-minute contribution. Bye-bye.
Bye-bye. Thank you all.
Thank you. Bye. So, Dr. Feng, see you in 25 minutes.
Yep.
Okay.